So, greetings for the day. This is a paper presentation on the topic dual pivot quick sort for the subject advanced data structures under the generous mentorship of Dr. Sudhir Sharma. This project is represented by Namish, Narayan and Neelesh Rajpurohit. So let's begin. So first of all, what is sorting? Sorting is any process of arranging items systematically. So sorting data is one of the most fundamental problem in computer science, especially if the arranging objects are primitive ones, such as integers, bytes, floats, etc. Since sorting methods play an important role in the operation of computers and other data processing systems, there has been an interest in seeking new and better algorithms than the existing ones. So we are comparing sorting methods by the number of the most expensive operations, which influence on effectiveness of the sorting techniques. Comparison swaps. So let's discuss what are the common sorting algorithms we have read so far. So bubble and shell sort. Just exchange two adjacent elements if they are out of order and repeat until the array is sorted. Then second is insertion sort. It scans successive elements for an out of order item, then insert the item in the proper place. Selection sort. It finds the smallest element in the array or the biggest element in the array and put it in the proper place. Then it swap it with the value in the first position and repeat until array is completely sorted. Merge sort. It divides the list of elements in two parts and sort the two parts individually and then merge it. Now we shall discuss QuickSort in detail because whole project is basically on the time complexity of QuickSort. So QuickSort. QuickSort algorithm is an effective and widespread sorting procedure with C into N into log n operations, where N is the size of the arranged array. So classical variant of the QuickSort algorithm is as follows. We pick an element called a pivot from the array, reorder the array so that all elements which are less than the pivot come before the pivot and all elements greater than the pivot come after it. And equal values can go either way of the pivot from the pivot side. After this partitioning, the pivot element is in its final position. Recursively sort the sub-array of lesser elements and the sub-array of greater elements. So can we make it more efficient? So yes, we can make it more efficient, and let's discuss how we can make it more efficient. So QuickSort basically takes C and log n operations. The problem is to find an algorithm with the least coefficient C, because for the larger values of C, the QuickSort algorithm will take a large time complexity. So the answer we have found is dual pivot QuickSort algorithm. So before going in deep, we first discuss what is the history of dual pivot QuickSort. So in 2009, the scientist named LNMIIT proposed the new dual pivot QuickSort implementation. So in the Java core library mailing list, he initiated a discussion claiming his new algorithm to be superior to the runtime library's sorting method, which was at the time based on the widely used and carefully tuned variant of classic QuickSort by Bentley and McLaury.
So, dual pivot QuickSort. The new QuickSort algorithm uses the partitioning a source of array, and where the T is the primitive type such as int, float, byte, char, etc. So it divides the array into three parts with the help of two pivot elements, which are the left pivot element and the right pivot element. So this is how the array looks like before partitioning: left pivot element, then the array elements, and the right pivot element. So after selecting our pivots, we begin partitioning the array into three parts. The first part, all the elements will be less than the left pivot. In the second part, the elements will be greater than or equal to the left pivot and also be less than or equal to the right pivot. and in the third part all the elements will be greater than the right pivot element. Then we shift the two pivots to their appropriate positions as we see in the below bar. And after that we begin quick sorting these three parts recursively using the same method. So after partitioning, our array would look like, first we'll get the elements that are less than the left pivot, then the left pivot itself, then we have the array elements that are greater than left pivot and less than right pivot, then the right pivot element, and then we have the array elements that are greater than the right pivot. So that's how the basic algorithm of dual pivot quicksort works. So here is an example to for this algorithm of dual pivot quicksort. So we take an array. So we assign the left pivot as the leftmost element, that is 24. We assign the right pivot as the rightmost element, that is 57. Now we find out the elements that are less than the left pivot, that is 24. So we have only one element, that is 8. So we position that element on the left side of the left pivot. Then we find the elements that are greater than 24 and less than 57, and we position them in the middle part of the array. And finally we find out all the elements that are larger than or greater than the right pivot, and then we arrange them in the third section. Now so now we see that the left pivot and the right pivot are in order as per the three sections are considered, and now we again apply the same algorithm recursively on all the three sections. So the first section is already arranged since it has only one element. On the second section we can see that again the left pivot and the right pivot are chosen, and then it's the partitioning is done and the array elements are arranged in order. So this is how we are applying the algorithm. So next, what now? So let us assume that the input data is random permutation of n numbers from range 1 to n. So upon running these algorithms, both the dual pivot quicksort and the classical quicksort, we found out some results. So for dual pivot quicksort, the average number of comparisons were 2 n log n, and the average number of swaps were 0.8 n log n. Whereas for the classical quicksort, the average number of comparisons were 2 n log n and the swaps were 1 n log n. So we see the difference in the number of swaps. So dual pivot quicksort has comparatively less number of swaps, that is 0.8 n log n, as compared to the 1 n log n comparisons of classical quicksort. This makes dual pivot quicksort about 1.25 times better in performance as compared to the classical quicksort. So now comparison and summary. While sorting primitive objects, it's more efficient to use the partitioning of unsorted array to three parts instead of uses of the classical approach. The more the size of the array to be sorted, the more efficiently the new algorithm works in comparison with the classical quicksort. The suggested dual pivot quicksort algorithm also works quicker than the classical scheme on the arranged array or the array with repeated elements. In a numerical experiment, 2 million random integers were sorted 50 times using classical quicksort and dual pivot quicksort, and the calculation times were analyzed. The results were as follows. The classical quicksort, the average time for the operation was 18.9 seconds, whereas the dual pivot quicksort, the average time was 16.5 seconds. So this is how dual pivot quicksort is comparatively better than classical quicksort. So the application of dual pivot quicksort. So what happens when we do array.sort in Java? So which sorting algorithm does Java use in the background? So the answer is, since Java 7 released back in 2011, the default sorting algorithm that they use in array.sort is the dual pivot quicksort. Earlier they used the classical quicksort developed by McClory, and after this Java 7 release, So they are currently using the dual pivot QuickSort. So room for improvement, yeah, always. So so what we can do to make dual pivot QuickSort more efficient is that while deciding the two pivot elements from the leftmost side and the rightmost side, to make it more better, what we can do is we can choose the left pivot and the right pivot from a subset of the array elements from the median. So we select a small number of elements from the median, and then we select the rightmost and the leftmost elements as pivots from that median set. So this was proven that this type of algorithm would work more efficiently as compared to the dual pivot QuickSort, classical dual pivot QuickSort. Okay, so this is how we can improve that algorithm even more. So thank you.